Welcome to AP Daily. This is Mr. Burris, and today we're looking at topic 2.8, tonicity and osmoregulation. So, what will we be learning today? We're going to look at how does water potential impact the movement of water? How does solute potential impact the movement of water? And finally, how do organisms maintain water balance? So let's dive in. Water potential measures the tendency of water to move by osmosis. It is calculated from pressure potential and solute potential. Water potential is represented by the Greek letter psi. And the unit of pressure is called bars. So water moves from an area of high water potential to an area of low water potential. The values of water potential can be positive, 0, or even negative. So the more negative the water potential is, the more likely water will move into the area. So if water potential is equal to -3 bars inside a cell and outside the cell, water potential is equal to -6 bars, the water is going to move from inside the cell to outside the cell due to the fact that -6 bars is more negative than -3 bars. Water potential of pure water has a value of 0 in an open container because there's no solutes, plus there's no pressure due to it being in an open container. Osmoregulation allows organisms to control their internal solute composition and water potential. So increasing the amount of solute in water will cause an increase in solute potential, but a decrease in water potential. Increasing water potential will cause an increase in pressure potential, and decreasing pressure potential will cause a decrease in water potential. So in an open system, the pressure potential is 0, so water potential is equal to the solute potential. Solute potential is equal to -ICRT. This formula is located on your formula sheet, so there's no need to memorize it. You just have to be able to use it and understand it. So for the formula, I is equal to ionization constant. So sucrose is equal to 1 and salt is equal to 2 in terms of ionization constants. C is equal to molar concentration. Molarity is the moles of solute per volume of a solution. So how much sugar is in water? R is equal to a pressure constant of 0.0831. That constant, that number, is located on the formula sheet. And finally, for temperature, temperature is in Kelvin. So you take the temperature in Celsius plus 273 and then plug it into the formula. However, an important thing to remember, the addition of solutes is equal to a more negative solute potential. So let's look at an example. A new tree is planted in a soil with a water potential of -4 bars. The roots of the tree has a water potential of -8 bars. Which way will the water move? Well, water will move from the soil into the roots since the soil has a higher water potential than the roots. So let's practice. For today's practice, we're going to be looking at statistical tests and data analysis. You're going to perform some mathematical calculations around water potential. So for this practice problem, what we would like you to do is pause your video, read the question, use the formulas, and figure out what is the water potential. When you finish, push play, and we'll discuss. Welcome back. For this question, you're looking at what is the water potential of a 0.5 molar sucrose solution at 21 degrees Celsius in an open system. For water potential, you have two equations. You have water potential equals pressure potential plus solute potential, and then you have solute potential equals -CRT. So the first step you should have done is solve for solute potential. So for this problem, you know that 0.5 molar sucrose solution is at 21 degrees Celsius. So the ionization constant is 1 because it's sucrose. The molar concentration is 0.5. The pressure constant, R, is 0.0831. And finally, the temperature is going to be 273 plus 21. When you plug those numbers in, you should have come up with a number of negative 12.22 bars. So now we've come up with the solute potential. Now we have to look at the other part of the problem, which is pressure potential. The pressure potential, in this case, depends on the system. In this case, it's an open system. An open system equals a pressure potential of 0. With that being said, you know that the solute potential was negative 12.22 bars. So your final answer is a water potential of negative 12.22 bars. So what should you have taken away today? Well, first, water moves by osmosis from areas of high water potential to areas of low water potential. Water moves by osmosis from areas of low solute potential to areas of high solute potential. Osmoregulation maintains water balance and allows organisms to control their solute composition water potential. Well, I hope this video was helpful today. Until next time, thank you.